his work involves computational intelligence and the philosophy of computational intelligence, and I think he's going to present to us some ideas in this area and a look at how the interaction between machines and humans could develop and whether we need to be worried about it or not.
Thank you very much. It's always very difficult when you're asked to give a presentation of this style to sort of think about what level to pitch the presentation. So I must apologise first of all if some of the things I'm going to say are absolutely obvious to everybody in this room and you know them all already. Hopefully you won't be too bored in the next hour, but hoping to at least some of these ideas might be new. I should say a little bit more about my background. And now, work at Goldsmiths College, where I held this chair of cognitive computing, and I'm particularly interested at Goldsmiths on sort of foundational issues about artificial intelligence and about robotics. But prior to moving to Goldsmiths, I used to work at the cybernetics department at the University of Reading in the UK, and there I did lots of hands-on work with real robots, so that's my sort of genuine robotic heritage. Now I'm not going to be talking today too much about the details of how robots work, or how you might design a robot, or how you might use a robot in the class. So again, I apologise if you're expecting to get any of that kind of information. What I'd like to take you through today are some examples about how robotics and artificial intelligence has become completely ubiquitous in our world, and then look at some of the Hollywood notions of robots. This notion you might have all seen, has anybody here seen the Terminator film? My lecture style is quite interactive, so I'm really sorry, I'm going to ask questions and I hope we'll participate in the spirit of the thing. Who's seen the Terminator series of movies? Pretty well everybody. And what's the basic premise of the Terminator series?
Protect people against the mean machines.
Yeah, well, I think the sort of the evil premise is that the robots are going to take over the world. And while I was at the University of Reading in the cybernetics department, my head of department there, quite a well-known guy in the field of robotics, a guy called Professor Kevin Warwick, made a lot of media headlines by pushing out this claim that one day, perhaps not too distant future, robots really would and could take over mankind. So this is an issue that's been concerning me for some time because I had some reservations about Kevin's claims. And that's kind of what I'm going to take you through at the end of today's presentation to you today. So I'm going to give you some videos about lots of videos, so not so much of me talking thankfully, but lots of videos about some state-of-the-art, as I see them, robotics projects. Then I'm going to bring you to what I see as a fundamental problem with robotics in the context of human interactions. And this is the problem of machine intelligence or artificial intelligence, as you might have come across the phrase. And I'm going to suggest to you that the problem of getting genuine machine intelligence is the key problem that's, if you like, holding back robotics for the good, perhaps stopping robots take over the world. But conceptually and philosophically, it's a really important problem, and a key philosophical issue. Can we ever genuinely say that a machine can be intelligent? Can I take a straw poll of hands at who around this table thinks that at some point in time, whether it's 10 years, 20 years, 50 years, 100 years, we will have a computer that will genuinely be intelligent? Can you raise your hand if you think that's going to happen?
How do you define intelligent?
I'm going to come on to that in a minute, sir, in my presentation, but we'll just use an everyday definition, any definition you wish to apply. So probably about a quarter perhaps of the people. Also, a philosopher called John Searle has suggested that we can never really genuinely get machine intelligence if you haven't really also got some kind of machine consciousness. So we need to be able to bring concepts into consciousness to think about them and analyse them properly. So does anybody here think that a machine, qua computations, will ever genuinely be conscious? One, the group's getting smaller, two perhaps. Well, it's against these sort of positions that I'm going to present a well-known philosophical argument at the end of my presentation that sort of suggests that purely in virtue of carrying out computations, a machine can never really be said to understand. And prior to that, I'm going to talk about something that I'm sure some of you, if not all of you, will have heard about, and that's a very famous test put forward by an English mathematician in the 1950s, a guy called Alan Turing. And he's synonymous for many things, he's a bit of a polymath. And one of the things he's synonymous for is the Turing Test for machine intelligence. And I'm going to spend some time talking about that. And the reason for talking about that is that my brief, when I was invited, and I should also, thank you very much for the invitation to present these ideas to you, but my brief when I was invited was to sort of give a presentation of about an hour, then also think of some kind of workshop. Now, I haven't brought any robots to work with you on in a sort of normal robotics workshop way, but I've got a thought experiment I'd like to play with you, and that develops from the Turing Test. But to be honest, actually, the Turing Test developed from this thought experiment. It's actually a Victorian parlour game, and I wish to play this game with you today at the end if we have time, depending on how long the presentation takes, because I think it's a very, very important game. Firstly, it will show you some foundational issues about what it is for a machine to think in the eyes of Alan Turing. But secondly, this game is going to highlight what I think are some very important skills that all young children should have when they are let loose on the internet. Of course, on the internet, as we're all aware, there's some very wonderful and lots of great information, but there's also some very unpleasant people out there who seek to do harm to children. And I think knowledge of this game, something called the Imitation Game, I'll talk to you about it later on, is a good skill for children to have to help them defend themselves against predators on the internet. So that's kind of where the workshop's going to go if we have time at the end of the presentation. And I hope you'll all participate in that workshop in the spirit that I'll present it to you. So without further ado, this talk's going to be about zombie robots and killer droids. Well, it's just a simple observation that as the years go by, it seems more and more true that computers are integrating themselves ever more into our lives. It wasn't so long ago that we had the first stock market crashes initiated by automatic trading by computer. Similarly, these days we're completely familiar now with the notion of an all-pervasive telephone network. Now, once upon a time, that network was fixed to fixed points in towns and cities around the globe. But now, with the advent of fast 3G mobile data networks, we've got access to a very fast and efficient telephone network that spans quite a large area across the planet. It seems that telephony itself is becoming more and more ubiquitous, and computers which control this network seem to be taking ever more control of our lives. Linked together with the rise of the telephone over the last 100 years, we also have in the last 30 years the rise of the internet. And the internet now has become just as much as an essential business tool as the telephone is. It's almost inconceivable to think of any business that wouldn't benefit from an internet presence. And on the tube this morning when I was coming over to this meeting, I spent a few minutes trying to think, well, are there any businesses left in the UK that don't have any internet presence or wouldn't benefit from it? And I couldn't really think of one. The internet's getting that ingrained in our lives. But what's one of the strange things that you might hear said about the internet is that the internet in its initial instantiations as the darknet in America was a network of networks that was designed to be very robust, a network that was indeed designed to withstand nuclear attack. So with the development of the internet and with its spread across the world, we now have a system, an electronic system, a networking system, that really we haven't got, no one person has got control of. It wouldn't be easy for Gordon Brown to turn the internet off. It wouldn't be easy for President Obama to turn the internet off. We have this thing that's very, very difficult and kind of, in some sort of spooky way, devoid from overall human control. Now, you're probably all familiar with the notion of the robot. The robot, as I've defined it, is an electromechanical machine which is guided by a computer or some kind of electronic programming device and is able to do tasks on its own. Now, the word robot was first introduced by the Czech writer Karel Čapek in his play R.U.R., Rossum's Universal Robots, which was published in 1920. And in that play, action began in a factory that made humanoid artificial people, which Karel called robots. I guess the notion of an artificial, non-human agent in the world could be traced even further back, and I'm treading on dodgy ground amongst this company, but I'm guessing the notion of the golem isn't a million miles away from, in some ways, from what we might think of as a robot. But certainly, Capek is the person that's most synonymous with the use of the modern word robot. Now, traditional robotics, and I would hazard a guess, there was a book that was shown from a seminar that was held here, what was it, in 1987?
83.
Sorry, I'm very deaf.
1983.
1983. Now, my intuition is that when you had this seminar, was this an AUT seminar? Yeah. When you had this AUT seminar then, that pretty well all the robots you were looking at were based in some way on this overarching execution cycle. Traditional robotics is based on the notion that we're somehow going to sense our environment, we'll get data from the environment, we'll do some planning, and then we'll get the robot actuated to move in a certain way. That we call the sense, plan, act cycle. So traditional robotics uses sensors. Now these sensors may be visual, there might be some electronic camera, they might use range data, they might use a laser range scanner. The robot you're going to see shortly does just that. They might use ultrasonics to work out the distance from the robot to a particular target. Using these sensors, the robots can obtain relevant information about their environment. When the robot's got useful information about its environment, if it's a mobile robot, for example, it might wish to build a plan for this local area so it can plan a route around the local environment. There'll be some AI software, which, if we're talking about a mobile robot, might have a path planning algorithm that might work out a route for me, for example, to walk around this table. And then once we've obtained our plan, we'll then execute that plan by passing relevant commands to our actuators, which might be robot limbs, might be robot grippers, they might be robot wheels. And that sense, plan, act cycle is iterated. Constantly the robot will sense the environment, plan some actions, act upon them, and then repeat that cycle again. And that's what I tend to think of as good old-fashioned robotics. And one of the first large robot projects I was involved with, called the Scenario Project, used just this methodology. Now I'm just going to take a breath for a few minutes and show you a little video about the Scenario mobile robot. Now this was a robot project that was commissioned in the late 80s. It was instigated in the early 90s, and the motivation was to try and design a robot wheelchair for paraplegic patients. So we could move, so people who have no notional mobility could move safely about a known environment, say their house. So instead of having a carer to say, take me to the toilet, or take me to the living room, take me to the front door, they can communicate with the robot in some way, and the robot will drive them there. Now clearly in a typical home environment, there are lots of hazards. If the robot's going to be let loose on the first floor, it'd be critical that the robot doesn't go down the stairs, unless it's a humanoid kind of robot that can manage stairs, but this robot wheelchair certainly wasn't. So we have to have lots of safety critical systems in this robot, also carrying a very, very valuable cargo, a human being. And there's a group of institutions, both commercial wheelchair manufacturers, robot manufacturers, academic institutions from across Europe, involved in the research and design and implementation of this prototype robot for the Scenario project. I just want to show you the video here, but I'd like to keep it out. There's one thing I want you to try and take from this video, and that's one critique of it. I'd like to think, if you were to criticise this now, bear in mind this is looking at very old technology, but what would you really notice about this video? It lasts about 5 minutes, I should warn. have two modes of operation, totally autonomous, or it could act as like a protective automatic wheelchair, just like the sort of electronic wheelchairs that you see, but one which won't allow the user to drive in a dangerous way. It won't allow the user to drive downstairs, for example. So you have these two different modes of operation, semi-automatic, semi-autonomous, and totally autonomous. I can't remember in 1991 when this work was carried out just how many microprocessors were involved in this project. I think we had about 6 state-of-the-art IBM PC systems controlling this robot. At the top of the chassis you'll see the laser mounted, the laser rangefinders, which give us a with 2-dimensional slice of all the obstacles in the local environment. By using any sound command, so it might be that a grunt like might mean move left or take me to the bathroom, and E might mean take me to the living room. So we have different sounds of vocal utterance. We can train the user to move the robot around. Part of the EU, the work was funded by the European Union, and the funding obviously entailed having some field trials with real users, potential users. The project itself sterling in 1991, so a moderate sized project for an academic institution to get involved with. Well, as we have finite time, I'm going to kill the video now for a minute. And I'd like to ask you, you're critiquing that robot, what in particular might spring to mind? Anything, any particular drawback? If you're looking at that robot that might prevent you from wanting to use it in the home. Yes, size? It's big, yeah. That's a prototype possibly could come down.
Slow?
Yes! That's the key thing. We were using enormous processing power of the day, but this robot was so slow. I don't know if I've been paraplegic, whether the benefits of having this freedom to control one's own mobility around the home would have been worth the sheer tedium of the thing moving around a few centimetres at a time. It would have been so frustrating. Now, the speed, of course, as technology progresses, microprocessors get faster, memory gets cheaper. We could expect that over time this technology would get quicker, but it's traditionally been a big problem with this old-fashioned kind of AI, this sense, plan, act kind of AI. That it's used enormous amounts of processing power to do even the most rudimentary kind of things. So, around the same time, 1991, there was a seminal paper published by Professor Rodney Brooks at MIT. And this looked at an entirely different way of doing AI and robotics. If you think about the scenario wheelchair, that used laser sensors, ultrasonic sensors, to help it build up a rich and detailed and hopefully high fidelity model of the world. From that model, from the user's commands, the robot would have certain goals, like move around the room. It would then use AI, artificial intelligence, to try and work out how to achieve those goals, and then it would command its actuators such that the goals were realised. The sense, plan, act cycle. Well, central to that sense, plan, act cycle, you have this notion of a representation, the representation of the environment, which is fundamental to the robot's operation. Well, in 1991, Brooks suggested that it might be possible to get intelligent robotic action without using explicit representations. And this led to a whole new variety, a whole new school of robotics research, and Brooks called it the Subsumption Approach. The basic idea with the subsumption architecture is that instead of trying to build up a rich, high-fidelity representation of the world, we'll say, well, why not use the world itself? What better representation of the world can there be than the world itself? So instead of trying to build representations of the world, let's try and see if we can use the world itself. Now, the subsumption architecture is a very simple idea. It said, can we build really simple behaviours and then layer them one on top of the other and build ever more complex behaviours in our robots by the higher level behaviours subsuming a lower level behaviour. So we might have, for example, a low level behaviour that says move around the room and avoid obstacles. Can we implement that really efficiently without using complex representations of the environment? In the same way that an insect moves around the room without necessarily having a complex representation of its environment. Once we've got that basic behaviour, the avoid obstacles, can we build higher level behaviours? A higher level behaviour I'm going to illustrate in a second, if we have a group of robots, might be, can we get one robot to follow another, not bump into its colleagues and not bump into the wall? Now, these robots were built in 1991, around the time of the scenario robot. They had one very, very cheap and very, very low power microprocessor on board to implement a very simple learning algorithm, what's called a neural network learning algorithm. They very rapidly learned not to bump into the wall, and with a little bit of help from a teacher, they were taught how to learn a simple following behaviour. Now, if you watch these robots, the key thing I'd like you to take from this, compared to the other demonstration, is that these robots, with very low computing power, move quickly. In fact, I was in the Department of Cybernetics when the first one of our subsumption robots was built, and I was there for its very first test. And it was built using very high power motors that we used for radio-controlled cars. And we built the first robot, and we put it down on the floor, and we turned it on, and the robot zoomed and headed towards the wall. Its sensors detected there was a wall there, and it put the brakes on, but it couldn't brake in time, and the first demonstration was it smashing at full speed into the wall. We had to gear the motor down significantly after that. So basically, we can, using this new idea of using the world as its own representation, moving away from this old notion of sense, plan, act, we can build robots more cheaply that interact with the world much more fluidly and much faster. Now, influenced in part by the work of Brooks and his subsumption architectures, we have robots of that ilk integrating themselves into the house these days. And I gather we have one such robot here today. Is that correct?
Yeah, I've got one.
This morning,
Is that the vacuum cleaner, or the lawnmower, or the floor cleaner?
It's the vacuum.
Vacuum cleaner. And these robots, I believe they've got more sophisticated over the years, but in the initial development of these robots, they were very much built on Brooks's subsumption architecture. They would move around, not bumping into objects. They would move around the room and eventually map out where the room was, because they would subsume the high-level mapping behaviour onto that basic avoid the obstacle behaviour. And they would go around and hoover your floor, clean the floor, or mow the lawn. So we've got robots, simple robots, already in the house. The problem with those simple robots, though, is that in the human world of experience, to use a Heideggerian sense of world, we have the notion of a world being meaningful and useful for humans. And human worlds are designed for humans, typically designed for adult humans. So we have tables at a particular height. We have chairs at a particular height. Objects are designed to be manipulated by humans. So if we want to see more and more integration of robots into the human world, then they're going to have to work on our terms. And that means we're going to need machines that are going to be able to walk up and down stairs. Stairs are everywhere. If robots want to integrate in our life, we need robots that can walk up and down stairs. We need robots that can be able to open doors. We need robots going to lift objects, so they're going to have to be dexterous and have some sort of manipulators like arms. Well, Honda realised this many years ago and embarked on an incredible research programme. When I used to work at the cybernetics department in Reading, every year we would get undergraduates who want to design and build a bipedal robot. They'd read about these things in science fiction, that's what they wanted to do. They had no comprehension of how difficult that task is. It's not even trivial to get what we call a passive balance robot built. These are robots that will, if you disconnect the power, they won't fall over, they're statically stable. But humans are not passive balance robots, we're active machines. We need to use energy to stay upright and to move around. And to get robots that can be actively stable takes even more energy and much more sophistication in your control strategy. This is an incredibly difficult task. Honda pumped millions upon millions into developing the robot I'm going to show you next. Some of you might have seen it before, it's called the Asimov robot. The result of a very long research project, and I think it's one of the state-of-the-art robots that you can buy or see around the world at the moment. This thing can climb stairs. It can kick a ball, it can put, in that sense it can play football. It can move around, it can carry trays, it can put trays down on a table. It can do many things which we associate with as human tasks. I'm going to show you this one, dancing. Now this isn't a Hollywood cheat, this is a real robot moving. How smooth its operation is, how it can move around.
Needs to read the music in order to dance, or
Sorry, I'm very deaf and I can't hear what you're saying.
does it need to hear the music in order to dance?
No.
No?
One of the things about this, and this is an excellent point, what you're seeing this robot do is all being completely reprogrammed. So the robot's ears have designed this sequence of moves and they've told the robot to behave in that way. If there was suddenly appeared a great big hole in the floor by the robot and the robot had been told to move right, guess what would happen? It would fall down that hole because it would not react, it would not interact with its environment.
So it's not random what it's doing.
It's not random, no. These are actions that the robot ears are pre-programmed into that robot. But the robot is not genuinely sensing its environment and acting in appropriate ways. It's just following through a pre-taught, pre-learned series of manipulations. Now what I should have shown is, first of all, just to get something to do that, it's a huge task. It's taken, as I said, many millions on millions of yen, many millions of men and women engineers' hours on the design and construction of that device. The resources of a huge corporation to get that thing working. And they've now got a physical device that's pretty good as a bipedal robot, but it lacks this fundamental thing. The thing it lacks is intelligence. A relatively small child might not be able to dance quite as well as the Asimov robot, but a relatively small child is unlikely to move to the left when it sees a great big pit immediately to its left. So, I've taken you to roughly where state-of-the-art is on humanoid robots, and one of the things that's highlighted is at the moment we haven't really got the intelligence to drive these humanoid robots to the limit of their engineered capabilities. But I wanted to show you the humanoid robot because, again, that harks back to this dystopian vision from Terminator, the idea that we have humanoid robots out there to subjugate mankind. Well, if you want a robot to subjugate mankind, these robots have got to have weapons. And you might think, well, that's never going to happen. But of course it already has. I'm sure everybody here has heard of the cruise missile. The cruise missile is a robot. It's a robot that flies. And it's a robot that kills. And it's a robot that's used widely today. early cruise missiles used to work out their position real time by sensing their environment, falling back to that original good old-fashioned way of doing robotics and sensing on that. And they used to use lots of different transducers in the vision to navigate between known landmarks. Of course, since the development of the first cruise missiles, we've had the widespread adoption of GPS network, and it was not that I'm an expert on cruise missiles, but to the best of my knowledge, I believe that later cruise missiles now cheat a little bit and just get their position, their localization in the world via access to military GPS networks. But I'm showing you this video to demonstrate what money, military money, lots of money developed in terms of robotic technology, and to give you some indication of the enormous destructive power of these military robots. And the question I want you to think about while you're watching this video is, at the moment these cruise missiles are controlled by a commander saying, I want that site destroyed, and executing a launch of a missile that will go on and, if it's successful, destroy that site. But just imagine if in some 10 or 20 or 30 years down the line, if artificial intelligence gets better, and we have missiles that, without waiting for a human commander to intervene, spot a threat on the horizon and go and destroy that threat without human interaction. Now, is that a far-fetched concept? Well, perhaps not. Oops, sorry. Because already, to use another science fiction, to draw on another science fiction metaphor, Robocop has entered town. In 2000, there was Professor, and I apologise for my, I'm not even going to try and pronounce the name, my appalling pronunciation of this Thai professor. Pretty, can anyone speak Thai and pronounce that? Save my huge embarrassment? No one's going to be brave. But this guy, at King Mongkut's Institute in Bangkok, developed a robot guard that would patrol a vehicle, an installation, warehouse, military installation, police station. And if armed appropriately, if it saw an intruder, it could ask the intruder to stop, and if the intruder didn't stop, it would open fire without waiting for its human master to intervene. This initial idea that was then commercialised by Samsung in Taiwan, and this video, I'm sorry I haven't got the sound for this, but you can see here a commercial version by Samsung of a robot guard that will open fire if it detects an intruder. That thing's a machine gun kicking off.
Who is posing for an intruder in the demonstration?
Sorry, I can't
Who
hear.
is posing for an intruder in the demonstration?
Always new people are coming.
When I was getting the videos together, this one originally did have sound, but unfortunately Windows in its all its glory managed to remove the sound when I was loading the video into my PowerPoint. But you'll see the system, I don't know if you can make it out, locating human intruders, throwing a box around it. These are people at night. If challenged, if they don't stop, it's trivial for the robot to...
If it's an animal, for example.
Well, I only know the company sales brochures. Well, the company line is that this thing can reliably detect humans. My own belief is I'm a little bit
Even
more
if it's
sceptical.
a child, for example, or any kind of human.
I would be sceptical. My perspective is I'm very sceptical of the claims of this machine. I'm presenting a company position at the moment. Samsung's position is that they've developed this robot guard. I'm not convinced that, personally, how reliably it will be able to detect humans from animals, or humans from small children, for example. But I just use it to illustrate that we already have a large industrial corporation taking this idea of a robot guard seriously, developing something that really will shoot without human intervention. So then, if this works as well as it said, as the makers claim, you can imagine if this AI technology is linked in with cruise missiles, perhaps this notion of the Terminator is not so far-fetched after all. If we have networks of computers that are intelligent, can sense their environment, can instigate active aggression on their own volition, we're not getting very far from this notion of machines taking over the world, it seems. I think I'll stop the video at this point. So is the Terminator really waiting? That's a scene, as you might be aware of. The Terminator, our humanoid robot, armed with a big fat gun, not a million miles from the Taiwanese robot with the gun we saw in the last video. Is this scenario of robots aggressively taking over the world, and is it really that likely? Well, before I critique this notion, I want to show you one last final video, and after this I think we're pretty well done with the videos today. My voice will have to grip it for the rest of the session. But I wanted to show you what I think is one of the most amazing, it's again military funded, it's developed by a firm called Boston Dynamics, one of the most amazing robots that I've seen recently. It's called Big Dog. Again, it's a very famous video that some of you might have seen on YouTube. It's powered by a small one-stroke petrol engine. You see this robot is moving over very rough terrain, not terrain we automatically associate with that robots can move freely across. And it's carrying quite a large payload. This robot is designed for the American military to act as a robot pack horse, to lug large weights across difficult terrain. This is quite astonishing. Look at the human kick the robot and see that the robot does not fall over. And that's an incredibly lifelike response of the robot. This is on ice as well, I should add. That's filmed on ice. Here we have Big Dog working in snow.
It's not that smart. On the left it's much easier to go.
And going up a snowy incline.
Noisy.
Mark, why is this such a strange shape?
It's like a flat open.
Like a llama.
Why is the robot such a strange shape?
Yeah, why it's not on wheels, for example?
Well, on wheels, I don't think it would be able to cope with this terrain. It's a lathe robot, and it's been designed to work in the worst possible terrains and carry a large load. And legs have been found to be the best means of moving over very rough terrain. If you've got great big troughs and ditches, very difficult for a wheeled machine to walk over. Again, this is all ice. I found this absolutely astonishing to watch. The engineering.
And also you can frighten the enemy.
Very true.
More than big dog, big fly. Or something.
Could go through water. I mean, I should add. And it can run, it can jump over little fences. I think we're going to see that.
Is being remote controlled?
That's something I'm going to come on to in a second. Getting a wheeled machine to walk over debris like that would be virtually impossible. When it falls, it doesn't. We don't have a catastrophic situation. The machine can recover.
But if it's entirely falling, can you get up?
Yes.
Yeah.
Can it crawl?
No, it must move on its face like this.
And die and roll over?
jump. So if you had to cross, how would you get a wheeled machine if that was something that was sensitive to the machine going over it and perhaps executed a bomb when it was triggered? You'd have a problem there with a normal wheeled or tracked vehicle, that this machine can leap over the obstacle. Now, the question that was asked was, how is that robot controlled? And I'm aware of two means by which Big Dog can be controlled. The first means, the means that it is primarily designed to be controlled, is by having an infantryman having a special backpack on their back with some special strips on this backpack, and the robot dog follows its human leader. Works out where the human is, looks at its terrain, works out the hazards in that terrain, plots a plan, again using this more traditional good old-fashioned sense plan out cycle, and then executes a series of actions to get the robot from where it is to where its human leader is. The other means of controlling Big Dog is to use basically a joystick controller, so we can have TV mounts on Big Dog and send Big Dog into hostile territory without a human being there first. Now again, I think that video is astonishing for the sheer technology that's involved in Big Dog and the engineering that's gone into making Big Dog work. As an engineer, I'm astonished by what these people have achieved. But one thing they haven't achieved very well still, where Big Dog is still lacking, is any general intelligence of itself. It still needs a human to say what to do, where to go. So Big Dog is still primarily reliant on human intelligence. So we still can see the best of the physical robots, the Honda bipedal Asimo dancing robot that I showed you, and the Boston Dynamics Big Dog robot that I showed you. The engineering far outstrips the artificial intelligence that controls these machines. They're still relying on humans. Now, you're going to ask, I'd like you to ask yourself, is that always going to be the case? Or is there some sort of conceptual barrier that will mean machines can never be intelligent as humans, and therefore we're always going to be safe from a Terminator-style scenario because always humans are going to have to be in control?
As we know today, the equipment becomes smaller and smaller and smaller to build a very sophisticated computer. So if you want to make a robot like a man, you need a brain of a man. With the equipment that we have today, the technology, we can build the brain of a man, but the size will be like a moon. This is written in all the research. So you can build a brain of a man with electricity.
This is why I'd like, and what I want to do for the rest of this seminar, before the little workshop session at the end, is to take you through a very famous philosophical argument called John Searle's Chinese room argument, that if true, will a priori demonstrate that a computer can never genuinely understand, no matter how big the computer, no matter how much you might have a computer simulating a brain. It might simulate a brain, but never really be a brain. In the same way that, for example, the simulation of gold doesn't make us rich unless that simulation is a duplication. The simulation of a rainstorm in a meteorologist's computer will never make you wet, again, unless that simulation becomes a duplication. And the argument, which I hope to have time to run through with you, if it's true, purports to show that there will always be a conceptual barrier between human understanding of scenarios and machine understanding of scenarios. And in a sense, that might lead us away from this notion that we can develop robots with genuine teleology, with genuine goal-directed behaviour. There's a great book about this argument, by the way, written by yours truly, Bishop and John Preston, called Views into the Chinese Room. It's something I've been interested in for many years. And if the argument, when I present it to you, interests you at all, then it's something you might wish to go and have a look at. But before we get onto the Chinese room argument, I want to take you back in time. Because the question, can machines really think, is an old question. It was a question that was posed in a seminal paper by the British mathematician Alan Turing. The paper was called Computing Machinery and Intelligence, and it was published in 1950 in the philosophy journal Mind. You can get this paper very easily on the internet, download it for free, or if you wish you can buy a collection of papers by Margaret Bowen called The Philosophy of Artificial Intelligence. Now in Turing's paper he stated that in his opinion the question, can a machine think, is simply too vague to be worthy of serious scientific study. And so he recast the question in the form of a procedure, a behavioural test, a procedure that has since become known as the Turing Test. And the Turing Test itself, this procedure that Turing specified for answering the question, can a machine think, was itself derived from an old Victorian style game, like the old Victorian parlour games that were very popular in Britain 150, 200 years ago. Now the game that Turing bases his test on is called the Imitation Game. And if we have time, I'm going to come back to this in the workshop session at the end of this talk. The game runs like this. Imagine the days before television. Imagine the days before radio. Days when on an evening after the work was done there'd be limited scope for entertainment. So imagine you're sat at home in a big house, a nice roaring fire with your family, wondering what to do. Well, this is one game that you might have played with your children or your friends and family. The game involves a man and a woman. And you ask the man and the woman to go into two separate rooms in your house. And then either you, on your own, if there's only you left, or perhaps a group of people, act as an interrogator. What the interrogator or interrogators are allowed to do is put questions to the people in these two rooms. Now, these questions are written questions, they're like typed out, so there's no hint of anything by the calligraphy of the question or the calligraphy of the response. So the interrogator thinks of a question, writes it out very formally or types it out, passes it through a letterbox in each of the doors of the two rooms or under the doors. They'll get a response to the question from the two people in the rooms, the man in one room, the woman in the other. Remember, the interrogator doesn't know who's in which room. And the aim of the game for the interrogator is purely by asking questions and getting text answers to try and work out which room the man's in and which room the woman's in.
Which kind of question?
Now the interesting thing is the questions can be about anything. So you might think, well, it's easy this, why is this at all interesting? Just say, are you a man? Yeah. But
Yes.
the respondents
Yes.
are allowed to lie. And that's what makes it tricky.
Are they allowed to lie?
They're allowed
Any
to lie.
question?
So the interrogators can ask any questions, but the respondents do not have to answer truthfully. The respondents win the game if the interrogator incorrectly guesses the gender of the person in each room. So the respondents win by the interrogator getting it wrong, the interrogator or interrogators win by correctly identifying the gender of the person in each room. Now, I'm going to show you how, from this, Turing developed a test for machine intelligence. But before I do that, I want to just highlight why I think this imitation game, something I wish to come back to later, in itself is an interesting thing for educators to talk about with students doing ICT or anything else, because has anybody here heard of large online multi-user virtual worlds? Things like Second Life?
Yeah.
Anyone? Who's heard of Second Life? Put your hand up. Yeah?
Would use, huh?
Yeah? No, not saying have you played it, have you
Have you
heard?
heard about it?
Yeah.
Anyone heard of World of Warcraft? It's a game that young children are very keen on. The thing that unifies these games, Second Life and World of Warcraft, is that participants in the game are playing simultaneously with tens of thousands of people distributed across the world, linked via the internet. And they'll communicate with other characters they might meet in these virtual online worlds, typically by text. Now, it's a strange phenomena, and perhaps one day some sociologists will investigate this and tell us why this happens. I don't have no reason why it happens. I can offer you no reason why it happens, but it's a simple fact that many of the characters players meet in Second Life might make out they're female when they're actually male, or they might make out they're male when they're actually female. And every time a person in Second Life or World of Warcraft interacts with somebody, they're effectively carrying out the imitation game for themselves. So this game has been redeveloped